Yeah, we have so we have a debate. How long is it?
Imagine trying to...
It's 23 minutes. Let's do it 1.2, so 20% faster. And so this is notebook LM, and we will load, because that's 23 minutes. So what is it? 25% of 23, whatever that is. And while it's playing, we'll look at this brain map. Well, it's nothing to do with the brain. It just the topics happen to be the brain, but the brain map is this thingy. While we're listening to the two bots debating one another.
Welcome to the debate. Imagine trying to reverse engineer a supercomputer, but instead of perfectly straight copper wires and silicon chips, it's made of 130,000 microscopic living wet noodles.
That is quite the visual.
Right? All tangled together, branching out and touching each other over 50 million times. You don't have a schematic.
No, you just have the physical wiring right in front of you.
Exactly. So do you expect to find a rigid, perfectly reproducible machine or a chaotic, highly individualized biological mess?
I mean, it is the ultimate test of how we understand biological complexity. Really, we are swimming in an ocean of data where the very definition of order is entirely up for interpretation.
And that brings us to the focus of our discussion today. The field of neuroscience has crossed a monumental threshold with the completion of the adult Drosophila, the Fruitfly whole brain connectome.
The Flywire dataset.
Right, the Flywire dataset. We are looking at a massive, fully reconstructed map of 127,978 neurons and all those 50 million synaptic connections. It is an absolute engineering marvel of modern science.
It is a staggering achievement, but it forces a profound question when we compare this new whole brain map to the previous subvolume dataset we had.
The Hemibrain.
Right, the Hemibrain. When you look at multiple brains side by side, have researchers actually mapped a predictable, highly stereotyped machine driven by genetic determinism, or have they captured a biological snowflake, like a completely unique entity shaped by stochastic development and its own idiosyncratic history?
Well, I represent the position that this connectome reveals a fundamentally conserved and reproducible architecture. Despite the organic packaging, we are looking at a biological machine with clear universal rules.
And I represent the contrasting perspective. I argue that the Flywire connectome exposes profound biological variability and that individuality completely challenges any rigid system of classification.
Let's lay out the core evidence then. The reason I argue that the fly brain is remarkably stereotyped really comes down to the sheer statistical consistency we are now seeing across hemispheres.
Across hemispheres and individual animals, yeah.
Exactly. When you look at the central brain, the number of intrinsic neurons differs by a mere 0.1% between the left and right hemispheres.
Which sounds small, sure.
I mean, think about what that means biologically. That is a difference of only 42 neurons out of tens of thousands. The developmental precision required for an organism to self-assemble with that level of symmetry is just staggering.
But you are heavily filtering the data to find that order.
Well, hold on, let me finish my point. While we can debate the weak connections, the data shows that strong connections have a greater than 90% chance of being conserved across completely different brains.
By strong connections, you mean the ones with more than 10 unitary synapses?
Right, or those making up more than 1.1% of a target cell's inputs. The underlying order is unequivocally there.
I see why you think that, but let me give you a different perspective. Wait, sorry, you had another point about the Princeton model?
Yeah, let me just add that we see this order validated by the new Princeton synapse model. Historically, tracing synapses in the fly brain was a nightmare because they are polyadic.
Meaning one single presynaptic transmitting wire branches out and hits multiple postsynaptic targets simultaneously.
Right, it's not a simple one-to-one connection. So to solve this, researchers developed an iteratively trained deep learning model that flipped the script entirely. Instead of looking at the complex outputs first, the AI was trained to hunt for the receiving ends, the postsynaptic targets.
A simple shift, but a big one.
A huge one. Using that model, we can now predict a neuron's exact type membership from its connectivity patterns alone with a 0.93 weighted F-score.
Which is a statistical measure of accuracy.
Exactly. A 0.93 essentially means that if you just look at who a neuron talks to, you get an A grade in predicting its exact identity. That level of predictive power simply does not exist in a biological snowflake. It exists in a stereotyped blueprint.
Well, I come at it from a very different way. I look at this exact same data and I see a brain that is far more individualized than the field ever dared to assume.
How can you say that with a 0.93 F-score?
Because you mentioned predictive power and stereotypity, but if you actually look closely at this data, your first instinct might be to panic. We have to confront the shocking reality that emerged when Flywire was compared to the Hemibrain dataset.
You mean the missing cell types?
Yes. 39% of the cell types originally defined in the Hemibrain simply could not be validated in the new Flywire dataset. That's over 2,000 proposed cell types.
Okay, but there is a very good reason for that, which has nothing to do with the biology itself.
Let me finish laying out the variability first, because it is not just missing cell types. Imagine mapping out a city, defining all the specific neighborhoods, and then you go to a second city that is supposed to have the same layout.
And
a third of the neighborhoods simply don't exist. They just vanished. When we look at specific functional areas like the Kenyon cells in the mushroom body, the total number of cells varied by an astonishing 30% across datasets.
the mushroom body is a unique case, though.
But it governs learning and memory. We are not talking about a symmetric difference of 42 neurons here. We are talking about massive structural variations in primary memory centers.
I still think the Princeton model proves the underlying structure.
But its very limitations highlight the inherent, almost chaotic complexity of biological wiring. Even with advanced neural networks, the model cannot reliably distinguish true autosapses.
Which is where a neuron loops back and physically synapses onto itself.
Right. Nor can it handle clustered axo-axonic synapses. The functional texture of the brain is actively resisting rigid standardization.
I think the best place to anchor our disagreement is on that 39% figure, the validity of the cell types themselves.
The 2,000 vanished cell types, yes?
You look at those missing types and see a failure of the machine blueprint. I look at them and see a massive triumph of the multi-connectome approach.
A triumph. How do you figure that?
By demanding that a cell type must have equal numbers across 3 distinct hemispheres. That's the left and right of Flywire and the original Hemibrain.
Okay, yes, they required consensus.
And by doing that, researchers successfully validated 3,094 consensus types. That is the largest biologically validated catalog of cell types in history.
I'm not denying the ones that matched.
But you can't just wave away the 3,000 that perfectly matched. The failure to match that remaining 39% isn't proof that the brain is a snowflake. It is simply an artifact of the Hemibrain's initial methodology.
How so?
The Hemibrain, by definition, was a single hemisphere. When the original researchers were classifying cells, they explicitly chose to oversplit categories in cases of uncertainty.
So they made too many categories?
Exactly. If you only have one specimen, biological taxonomy dictates that you err on the side of caution. If 2 cells looked slightly different, they lumped them into tiny, artificial subgroups based on minor morphological quirks.
And you're saying Flywire fixed that?
Right. When we finally got a second full brain to compare it to, those artificial, hyper-specific boundaries naturally dissolved. It's not that the biology is random, it's that our initial human categorizations were flawed.
I'm sorry, but I just don't buy that. Let me tell you why.
Go ahead.
You are dismissing the loss of a third of our recognized cell types as a mere, methodological oops. But the data tells a deeper story.
What's literally oversplitting, though?
Wait, if it was just oversplitting, you would expect those vanished cells to cleanly merge back into a parent category when you run across dataset connectivity clustering.
Right, which they often do.
But they don't always do that. They show highly complex clustering patterns that separate neurons from the same proposed type and recombine them with completely different ones. This demonstrates that inter-individual variation is massive.
I disagree that it proves massive biological variation. It's just taxonomy correcting itself.
Let me give you a specific physical counterexample that shatters the idea of a universal blueprint. Look at the visual projection neurons, specifically the VPN D3 lineage.
Ah, the spatial routing issue.
Exactly. In the Flywire dataset, the axons of these neurons in the right hemisphere take a standard, expected route to their target. But in the left hemisphere, the axon bundle loops completely over the mushroom body peduncle.
For the listener, the peduncle is a massive, dense stalk of nerve fibers right in the middle of the brain.
Right, so the left hemisphere wire takes a drastically different physical trajectory, going completely out of its way to loop over this central pillar. Yet it still ultimately finds the exact same target.
Which is incredible.
But if this brain is a rigidly stereotyped printed circuit board, how do you account for such gross anatomical asymmetry? A factory machine doesn't just decide to route a cable around the outside of the casing on every second unit.
That's an interesting point, though. I would frame it very differently.
How else can you frame a cable taking a completely wild detour?
Well, the physical wires might take weird detours, like your peduncle example. But the fact that the VPN3 lineage takes a completely different route and still reliably finds its precise synaptic target, that is actually an argument for stereotypy, not against it.
I don't follow that logic at all.
It proves that the developmental routing algorithm, the genetic instructions telling that wire where to plug in, is robust enough to overcome massive spatial perturbations.
Sure, but the physical routing is highly variable.
But physical routing is just the hardware casing. What actually matters is the software. If we want to understand the machine, we have to look at who is talking to whom.
Which brings us back to the connections.
Exactly. And when we look at the actual synaptic connections, I rely on the strong edge rule, which is just a filter. I see why you think that, but let me give you a different perspective.
It is a mathematically necessary filter. Differences in edge weights between hemispheres of plus or minus 30% or less can be entirely explained by modeled technical noise.
Technical noise like what?
Like variations in synaptic completion rates during the AI tracing, or the false positive and false negative detection rates of the algorithms themselves.
So slicing biological tissue nanometer by nanometer creates artifacts?
Exactly. When you filter out that technical noise, the core network, the heavy connections that actually drive behavior, is incredibly solid.
But you're erasing the details?
Theoretical models and empirical data from larval Drosophila show us that when you remove connections comprising less than 1.25% of a cell's input, the left-right asymmetries largely vanish. The core computational logic remains intact.
You're setting up a heuristic that conveniently ignores the vast majority of the biological reality right in front of us.
By removing literal noise?
Yes, if you only look at the strongest, thickest cables, of course the brain looks like a machine. But let's look at the reality of that detection pipeline you're relying on to dismiss the rest.
The Princeton model, you mean?
Right. It achieved up to a 0.23 F-score increase in highly challenging regions like the mechanoreceptor Johnston's organ neurons, which is commendable.
It's fantastic.
But even so, it fundamentally assumes a single presynaptic object per detected postsynaptic terminal. It forces a clean, machine-like assumption onto incredibly messy biology.
Because biology often follows clean rules at a macro level?
But the reality of the network is built on weak connections. Listen to this statistic. If you look at a connection, an edge, consisting of a single synapse and the hemibrain, it has only a 14% chance of being seen in both Flywire hemispheres.
Which I am arguing is largely developmental noise.
14%. And the vast, overwhelming majority of the 16.5 million edges in this entire connectome are weak edges.
But a single synapse isn't driving behavior.
By applying your strong edge filter and removing that 1.25% threshold, you are stripping away the functional texture of the brain.
I think that's a bit dramatic.
You are erasing the exact subtle, individualized wiring that likely accounts for a fly's unique behavioral quirks, its learned experiences, its stochastic development. You are actively erasing the snowflake to find the machine.
I'm not convinced by that line of reasoning because, just because my laptop has a few stray microscopic scratches on the motherboard or slight variations in the solder joints.
Biological synapses are not solder joints.
True, but it doesn't mean it operates on a fundamentally different computational logic than yours. The presence of noise does not invalidate the existence of a blueprint.
That is a compelling argument, but have you considered what happens when that developmental noise scales up to massive structural changes?
Massive structural changes? Like what?
We aren't just talking about a few stray microscopic scratches. Let's zoom in on the mushroom body again, the learning and memory center. This is where the stochastic development argument truly crystallizes.
Okay, let's talk about the mushroom body.
In the Flywire dataset, there is a specific type of Kenyon cell, the KCG-M cell. These cells are almost twice as numerous in the Flywire brain as they are in the hemibrain.
Yes, they doubled.
Think about the scale of that. We are not talking about a 14% variance in a weak synapse. We are talking about a 100% increase in a primary memory encoding cell population.
Which is a fascinating developmental anomaly.
It is likely driven by environmental factors, like protein starvation during the larval stage. This proves that the fly brain is highly susceptible to developmental and environmental perturbation.
It definitely responds to the environment, yes.
It is molded by the world it grows up in. If a fly goes hungry as a larva, its brain physically restructures its memory centers. How can you look at a cognitive center that physically doubles in size due to environmental conditions and still call this a rigidly predictable machine?
I am so glad you brought up the Kenyon cells, because the mushroom body actually provides the ultimate proof of the machine's underlying elegance.
How does doubling the cell count prove elegance?
You are looking at the form, the physical number of cells, and entirely missing the function. Yes, the Flywire brain has almost twice as many KCGM cells, but how does the brain respond to this massive developmental perturbation?
It just grows larger?
No, it engages in profound mathematical homeostasis. It brilliantly rebalances itself. Despite having twice the number of cells, the KCGM population mathematically compensates to preserve the exact same relative network weights.
You mean the network actively adjusts itself?
Yes. In the hemibrain, each KCGM cell samples from about 8.8 unique odor channels. This is a crucial network parameter we call K.
Okay, so K is 8.8.
Right. In the Flywire brain, because there are twice as many cells competing for the same input, the network perfectly reduces K down to about 5.8 unique odor channels per cell.
Wait, so the network actively suppressed the number of unique connections each cell makes?
Precisely. It reduces the sampling rate per cell to perfectly maintain its 32% presynaptic budget within the global network.
Wow.
It recognizes the excess capacity and tunes down the individual connectivity to maintain the overall system architecture. And even more beautifully, it maintains the exact excitation-inhibition ratio, globally regulated by what is known as the APL neuron.
Right, the APL provides global inhibitory feedback to the Kenyon cells.
Think of the APL neuron like a bouncer at a crowded club. The club, in this case the Kenyon cell population, suddenly doubled in capacity due to that developmental quirk.
So the bouncer has to work twice as hard?
Exactly. The bouncer mathematically turns down the volume of the music from the stage, so the overall noise level, the excitation-inhibition ratio, stays exactly the same across the entire building.
That is an incredible mechanism.
The network scales its connectivity so precisely that the functional balance of excitation and inhibition remains identical across completely different brains, despite a massive variance in actual cell numbers. That is not a snowflake helplessly blowing in the wind of environmental perturbation.
No, but
That is an incredibly sophisticated, dynamically adjusting machine that aggressively defends its core computational parameters.
while you call it a dynamically adjusting machine, I call it evidence of profound inherent plasticity.
Plasticity in service of a machine.
But you are acknowledging right now that the parameters, the fundamental connectivity rules, the number of odor channels sampled, the individual synaptic weights are totally flexible. They change dramatically from one individual to the next, based on how many cells happen to survive the larval stage.
But they change in service of a conserved goal. The equilibrium is the point.
The fact that the excitation-inhibition ratio reaches an equilibrium doesn't negate the fact that the underlying physical wiring, like the specific antenna lobe projection neurons connecting to specific Kenyon cells, is entirely different between these two flies.
It's different, but functionally identical.
The fly brain had to re-architect its memory center on the fly, no pun intended. If the wiring diagram has to fundamentally rewrite its own schematics to accommodate environmental perturbations, then the concept of a single universal connectome is an illusion.
It's not an illusion. It is a parameterized blueprint.
A parameterized blueprint isn't a single species wiring diagram that we can just print out and put in a textbook.
The overarching architecture, the fact that olfactory input always goes to the Kenyon cells, which are always globally regulated by the APL neuron, which then always output to the mushroom body output neurons. That architecture is absolute. It is universal across every fly.
But the execution of that architecture is where the biology actually happens. To understand memory or complex behavior or biological individuality, we cannot just look at the abstract block diagram of input goes to output.
We have to look at the macro rules.
We have to look at the specific connections. And when we do, the variability is staring us in the face. We see that 1/3 of assumed cell types couldn't be found across brains.
Which I still say is an artifact.
We see a 30% variation in the absolute cell counts of specific learning centers. We see a vast sea of millions of non-reproducible weak connections that don't pass your 1.25% filter.
Because they're noise.
They make up the unique functional texture of an individual's lived experience. The data demands that we view each fly brain as a highly unique entity. Yes, they share a body plan, but neurologically, they are individuals shaped by their own unique stochastic development.
Look, I hear you, but we must be careful not to mistake technical noise, slicing artifacts, and developmental compensations for functional individuality.
I don't think it's a mistake. Well, the multi-connectome approach has given us a lens to finally separate the true biological signal from the noise. And when we look at the signal, the rigorous validation of over 3,000 consensus cell types, the striking predictability of those strong synaptic edges,
If you filter for them,
the incredible 0.1% consistency in left-right cell counts in the central brain, and those elegant mathematical homeostatic mechanisms in the mushroom body, all of it points to a profoundly conserved blueprint.
we clearly see the data very differently.
The fly brain is a highly complex machine, yes, but a machine nonetheless, operating on mathematical rules we are finally beginning to decipher.
I think the only thing we can say with absolute certainty is that a single connectome is no longer enough to answer these questions.
I will definitely agree with that. We have officially moved past the era of the connectome and into the era of comparative connectomics. Future multi-connectome comparisons across dozens or hundreds of brains will be the only way to truly definitively separate the technical artifacts you were talking about from the genuine biological individuality I am pointing to.
On that, we are in complete agreement. The comparison of Flywire to the Hemibrain is really just the beginning of a much larger journey in neuroscience.
Absolutely.
We are finally building the comparative tools we need. And the incredible thing is, the listeners don't just have to take our word for it. The data is out there for the public.
It's all open source.
Right. Through open source tools like the Codex platform, anyone can navigate the Flywire Connectome themselves. You can trace the neurons, look at the clustered synapses, and explore the architecture firsthand.
It brings us back to where we started. When you look at that dense, tangled, beautiful map of 130,000 neurons, you have to ask yourself what you're really looking at.
Exactly. Are you looking at the ultimate biological circuit board, executing its genetic code with ruthless, homeostatic precision? Or are you looking at stochastic development in action, a completely unique reflection of a single life? We will leave that for you to decide.
Okay, that was Notebook LM. Yeah, we generated a bunch of resources. Yeah, I did the video. We did the video. The video was okay-ish. We had that map. It's kind of nice, but it's overly complicated. I would have simplified that. Yeah, I made 2 of these infographics. Yeah, I'm not sure about those. The question is, well, there's 2 things that are missing. I can do quiz. Quiz is kind of nice. Flashcards. Yeah, flashcards. Well, it's kind of the same as the quiz. The main 2 things that are missing is in the audio, they're meant to be an interactive mode where you could talk to the presenters, like intervene. So it sounds more like a discussion rather than, well, a dialogue in this case. I mean, the dialogue is pretty good. And it's kind of nice that they, it's in a debate mode, so it's not taking any specific side. So that's nice. But yeah, it would be nice if we could intervene into it as well, or just talk to the thing like separately in a voice model. So there's no voice model within Notebook LM. Yeah, we can do a report, which is a blog. I'm not sure if we're gonna do much more blogs. What we are after though is interactive simulations. I'm not, and again, there's no. The infographic is static, so we like simpler infographics, but ones that you can actively interact with. So if we could potentially generate some ideas and then get the coding agent to do an interactive simulation. Yeah, we actually have a prompt for it. Can it generate code? I don't know, we have a prompt like this. This is normally what we use for a coding agent. Okay, it's actually generating the code. Should we run it quickly? Well, that's what we're mainly after. We don't want static blocks or anything. Let's go Flywire. 400 lines. HTML with JavaScript embedded in it. Really had to do a bit of editing. Okay, what's the point? It's not really working, is it? Yes, that notebook. Clear brain. Play demo. It's not doing anything. Yeah, no, Notebook LM cannot code. Notebook LM cannot code. Don't even understand what it was trying to do. The simulation will visualize the leaky, integrate and via spiking neural network model after the Fruitfly brain Connectome in the small individual neurons, integrate signals from the partners based on synaptic weights. Okay, yeah, but the simulation is not great at all. So yeah, we'll look at it next time, see how we could improve that. Everything we do is available on bionicals.com. Go check it out. Provide your feedback, likes, subscribes, comments, mainly comments. That's what we're after. And I'll see you next time. Bye.